Welcome back, friends. In today's class, I'll talk about the spring energy and spring force. So let's take a spring here. So this is a closed coil spring. If I apply certain amount of load, because of this load, the spring will get pulled in the not downward direction. There will be an extension in the spring in the downward direction. So if I keep on increasing the load, there will be more extension in the spring. And what's causing this extension? Because this load is getting pulled in the downward direction because of the gravity. So I'm going to call it as Fg is equal to mg, and that is causing an equal and opposite reaction according to the Newton's third law, and the equal and opposite force is being stored in the spring. So that is called spring force, which is represented with Fs, and in terms of spring it is represented with the formula Kx. Now Fs is equal to Kx, and that is spring force, Fs equal to Kx. And you can also say that because Fg is equal to mg and both these Fs and Fmg are equal, so I can say it Fs equal to Fg, which is equal to Kx equal to mg. Now you can see this, if I talk about the direction, because there is a directional force is a directional quantity and displacement is also a directional quantity. So let's say this displacement is the displacement of the spring, in this case is negative. Negative 10 centimeter. I'm going to take an example. Displacement of the spring is 10 meters because it is acting in the downward direction, so I'm going to use the negative sign. So displacement becomes negative 10 meters. So I wanted to find the spring force. Spring force formula is equal to Kx with the negative sign. This is the formula you will be given in your formula booklets. So if this formula is given to you, so you will put a negative Kx, displacement is negative 10, and then force value will come out to be equal to whatever the K value is. Let's say it's I'm going to assume K value equal to 2.5. We haven't talked about the this spring constant. We'll talk about it later on. Right now we are trying to find the direction of the force and the spring constant. So this is negative times K value is 2.5 times negative 10, and then which is equal to positive 2.5 25, positive 25 newtons. 25 Newton. That's the force value which we come across. Now in this you might have observed here I didn't put the negative. I haven't used the negative sign over here. So what I wanted to tell you is that if you're going to consider the displacement, as negative, then you have to use the formula as F equal to negative Kx. If you don't use the displacement as negative, you just put the value as 10, then you don't need to put the negative sign and this negative sign in front. So this is 2.5 times 10, which is going to give you the force. So force equal to 25 newtons. And some books uses this formula, some books uses this formula. So depending upon whatever formula your book is using, you can use that formula, but I just wanted to tell you guys that it does not make any difference. So if I'm using, again I'll summarize this, if I'm using the direction for the displacement, the spring is getting displaced in the downward direction, and I'm finding the negative value of this, then I will use K equal to not K, F equal to negative Kx. F equal to negative Kx. This is the formula I will use. If I'm not using this direction, then I will use F equal to Kx. This is the formula I will use. Now because this spring is moving in the downward direction, so there is some energy which also gets stored in the spring. There is some amount of energy which is going to get stored in the spring. So we can find that energy value by using the formula spring energy Es equal to half Kx square. It is same as writing the energy is equal to force times distance. And if I use this formula and elaborate on this formula, and then I can reach up to this one. So I'm not going to get into the details of this, but we're gonna use this formula for spring for finding the spring energy. So now let's look into the question, one of the problems on spring energy. So the spring is stretched to a position of 35 centimeter from its equilibrium position. At the point of the force extend at that point the force extended on the spring is 10.5 Newton. What is the elastic potential energy? So elastic potential energy, we've just seen the formula, is equal to half kx squared. This is the formula for elastic potential energy. Now I haven't talked about this k also. K is called spring constant. Spring constant. And spring constant means, because it's a constant value, it means this spring constant depends only on the properties of the material which we are using. What kind of a material? Spring constant does not change with the elongation. So let's say this is a iron made or a steel made up of steel. This spring is made up of steel, and this is the same spring, this is the same spring, this is the same spring. So even if I'm going to change the load, the spring constant value, k value, will not change by changing the amount of load you are applying. That will remain the same. So that spring constant will depend upon whether it's made up of steel or plastic, or whether it's well, it's nothing, springs are never made up of plastics, but whether it's made up of iron or any other material. Okay, so let's go back to this question now. So k is the spring constant, and now spring is stretched to a position of 35 centimeter from its equilibrium position. So it's not told to me whether it's being stretched in the downward direction or the upward direction. So I can use, it's giving me the distance, how much distance this is being moving. So I can use force equal to kx formula. So I don't need to use force equal to negative kx formula. This formula I will use when it is given to me that it is moving downwards or upwards. The displacement is downwards or upwards. Now force equal to kx, and then I wanted to find the elastic potential energy. To find the elastic potential energy, first of all I need the value of k, because the displacement is given to me, which is 35 centimeter. Again I have to convert it into meters, so it will be 0.35 meters. I have this value. I wanted to find this value, but I don't know this value. If somehow I can find the k value, I'll be able to solve this question. So force, we know that force equal to kx. So is something given to us in terms of force? Yes. So I've been given the force value. Force is equal to 10.5 Newton. So again, no direction, it is not talking about the direction of the force. So I will use force equal to kx. K value will be equal to, I can easily find out, this is 0.35, and then k value will come out to be 10.5 divided by 0.35. That will come out to be, I have to do some calculations now, 1 second. So the k value will come out to be 30 Newton per meter. So 30 is the k value. Sorry. So this is Newton per meter. And we can also find out the units of k. Force equal to kx, and k is force, and I can write k equal to force divided by x, and then units of force is Newton and the units of x is meter. So k is, units of k will be Newton per meter. So this is the k value which we figured out. Now what we wanted to do is we wanted to find the elastic potential energy. So I'm going to file this value back in the equation which I've written over here, and then let's rewrite this equation. Es equal to half kx squared. So this is equal to half times k value is 30 and x value is how much? 0.35 squared. So if I'm going to calculate this value will come out to be, elastic potential energy will come out to be 1.84 again joules, because this is energy, and make sure you don't forget to square this value. So now that's the answer for part A. Now I'm going to do the part B. If the spring is, if the stretch in the spring is allowed to reduce to a 20 centimeter, what is the change in the elastic potential energy? So now I'm reducing the reducing the stretch to 20 centimeters. So I'm going to go in this question, I'm going to try and draw in the diagram. Earlier, this, let's say this is, oops, I have to redraw the, so this is the spring. Okay, now in the first instance, I stretched it to 35 centimeters, this much, 35 centimeters. Now the question says I reduced it to 20 centimeters. So read the question carefully, reduced to 20 centimeters. So what I'm going to do is I'm going to extend it to only 20 centimeters. Okay, so I've reduced by how much? Reduced by 15 centimeters because I wanted to reduce it to 20 centimeters. All right, this is the scenario. So I wanted to, will the K value change? Do I need to find the K value again? No, because it's made up of the same material. So I don't need to find the K value again. So we've already figured out the K value, which was 30 Newton per meter. I'm going to use that K value and try to solve for part B. So when the spring is stretched to only 20 centimeters, how much energy is stored in the spring? Energy stored, ES value will be half kx squared, which is equal to half times K value in this case is 30, and X value will come out to be, the displacement is 0.2 squared, and that is the spring energy stored when it is stretched only up to 20 centimeter. So the energy stored, if I calculate this value, this will come out to be 0.6 joules. Now when it was stretched to 35 centimeters, the energy stored was 1.84 joules. That's what we figured out. If I look into this value, that's what we found out. Now the new value is 0.6 joules, and the question is asking me what is the change in potential energy. So the change value will be change in potential energy. Change in potential energy is PE final minus PE initial. Initial was 1 point, final is 0.6 minus 1.84 joules. So if I subtract these two values, the value will come out to be -1.24 joules, which means the energy is being taken out of the system. Remember, energy given to the system is positive, energy taken out of the system is negative, so that's why the value is negative. So hopefully you were able to